So we are going to prove the classification theorem for finitely generated torsion modules over a principal ideal domain. So let R be some PID and M be a finitely generated torsion module. The end result here is we're going to show M is a direct sum of cyclic modules, which obviously is much easier to deal with and means we can get a lot of information about these types of modules. Now, in order to start this proof, we're going to begin with a lemma, which I'll call the annihilator splitting lemma. At first, it's not going to be obvious why exactly this is going to be useful, but we'll see later in the proof that it's going to come in very handy. So let's suppose we have some module n, which is a submodule of M. Therefore, we can construct the quotient module M mod n, and we're going to say that this is isomorphic to a direct sum of cyclic modules R times yi, where yi are the generators of this module. Now, this is not a theorem. We're just going to assume this to be true for this lemma. So if we suppose that the quotient module looks like this, we're further going to suppose that we have a map, psi, that takes all of the generators here, these yi's, into the original module M. And this psi is going to satisfy two conditions. First of all, pi composed with psi is going to be the identity map. So in this case, pi, this is the projection map that takes us from M to M mod n by mapping every element to its coset. So this is going to give us the identity function. And also, if we have some element in the annihilator of yi, then this is going to mean that A times psi of yi must also be 0. In other words, A also needs to be in the annihilator of psi of yi. If these two things are true, we are going to show that it means M is isomorphic to n direct sum with M mod n. So this is our goal given these two conditions. Now, the way we're going to prove that M is isomorphic to n direct sum M mod n is we're going to show that we can take this psi and turn it into a splitting. So the way we're going to do that is look at a map phi from M mod n into M, and the map is going to look like phi of R1 Y1 comma dot 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 comma Rn Yn. So these are one of the elements in M mod n looks like this. This is going to equal R1 times psi of Y1 plus dot 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 plus Rn psi of Yn. So we're going to take each element, replace it with psi of that thing, and we're going to add them all up on the other side. Our goal is to show that phi is a splitting. But the first thing we need to check is that phi is well defined, because we could have a case where R times yi is equal to S times yi, but on the other hand, R times psi of yi might not be equal to S times psi of yi. So to make sure phi is a well-defined function, we need to make sure that this implies on the other side R times psi of yi equals S times psi of yi. To do that, let's first subtract syi on both sides. So we're going to get R minus S times yi equals 0. Of course, this means R minus S is in the annihilator of yi. And this is where the condition for the splitting comes in. The reason we want this annihilator condition is actually just to show that this map is well defined. So if this is true, if R minus S is in this annihilator, then we know from the condition on psi, this means that R minus S times psi of yi equals 0. And then of course, we can add S psi of yi on both sides, and we get R times psi of yi equals S times psi of yi. So because of this, if we're looking at two ordered tuples that are equal, we have R1 Y1, S1 Y1, R2 Y2, S2 Y2, and so on, and those are equal, then we know that the psi versions are going to be equal, and then of course if we add them all up, we're going to get the same result. So this is showing us that phi is well defined. Now our goal is to show that phi is a splitting. So one of the conditions for phi to be a splitting is that we want the projection map composed with phi to also be the identity. So let's see if that's true. In other words, we're going to take this output over here, we're going to apply the projection pi, and see if we get back this ordered pair over here. So let's try that out. If we take pi of r1 psi of y1 plus dot 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 plus rn psi of yn. Now we know that pi is an R-module homomorphism, which means that we can bring it into each of these terms separately. So this is going to be r1 times pi of psi of y1 plus dot 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 plus rn pi of psi of yn. And we said one of the conditions on psi is that pi of psi gives us the identity. So this pi of psi of y1, that's just going to give us y1. This would essentially be the first component, and then everything else will be 0 for this term. And then this is going to give us, in here we'll get all the other terms, dot dot dot. Over here, this is going to be rn times yn. So when we take all of these and put them together, we do get back the original input to our function phi, and therefore pi of phi is the identity. That's the first condition for our splitting. All that's left is to show that phi is an R-module homomorphism, and then we will be done. So let's first look at what is phi of, if we add two elements in the quotient module here, then we can just add the things in the front. So this is going to be r1 plus s1 times y1 dot 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 rn plus sn yn. Now if we do this evaluation, we're going to get the same thing over here, r1 plus s1 times psi of y1 plus dot 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 rn plus sn psi of yn. And then on the other hand, let's look at what happens if we do the phi to each part. So if we apply phi to each of these parts separately instead of adding them on the inside, the result that we get is first r1 to rn times psi of that y, plus the same thing except we have s. And we know that in the original module, this stuff is all in m. We can distribute this out and move it around, and we'll see that we get r1 psi of y1 here, s1 psi of y1 here, and so on. So these two things are going to be equal. If we look at the other condition for an R-module homomorphism, looking at phi of s times something on the inside here, then we get an s on each of the terms. Whereas if we keep the s on the outside here, it's going to be a factor all the way on the outside multiplied to everything. We know that we can distribute in a module, so we know that these two are also going to be equal as well. So we've gotten that phi is an R-module homomorphism, and we also showed earlier that pi of phi gives us the identity, and therefore phi is a splitting. So from that we can conclude m is isomorphic to n direct sum m mod n. Again, the fact that we can conclude this from our splitting I showed in a previous video, so you can check the link in the description for that. So we just finished proving this first lemma. If we have some submodule where the quotient is this direct sum, and we have this map psi from the set of generators into the original module, where pi of psi is the identity, and anything that kills yi is also going to kill psi of yi, then we get m is isomorphic to n direct sum with m mod n. The next thing we're going to do here is prove one more lemma, and then we'll get straight into the actual proof. The lemma is that if we have some set of generators, x1 to xn, that generate our module, we want to show the annihilator of m, the entire module, is the same as the intersection of the annihilators of each of the generators. So basically we need to show if something annihilates everything in m, then it annihilates the xi's and vice versa. So first of all, if something annihilates m, well of course all of the generators are in m. So because these are elements of the module, if it annihilates everything, it has to annihilate the generators, and therefore it's going to be in the intersection of the annihilator of each of those generators. So we've proven this first direction very easy. On the other hand, let's suppose we have some element in our original ring that's in the intersection of these annihilators. In other words, we have some element that annihilates every single generator. Well, if we take an arbitrary element m in the module, we know that we can write it as r1 times x1 plus r2 times x2 plus dot 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 plus rn times xn. And the question is m annihilated by some element that's in this intersection? So suppose that A is an element in the ring that annihilates all of the generators. If we take A times m, that's going to be the same as A times r1 x1 plus A times r2 x2, and so on. Now we know in a PID, in particular, the ring is commutative, so we can switch these two, and we're going to get AX1, AX2, AXN for all of these generators. But we said A is in the intersection of all of the annihilators, which means that A times Xi, that's 0. So this part's 0, this part's 0, and so on. This entire thing is just a bunch of zeros. So AM equals 0, meaning A is in the annihilator of M. So that proves the other direction. If something annihilates all the generators, it also annihilates the entire module, and therefore these two sets are going to be equal. So remember, our goal is to show that any finitely generated torsion module over a PID can be written as a direct sum of cyclic modules. We're going to start by proving that in a simpler case. Now, we know because M is torsion that M is going to have some non-zero annihilator. There's at least one element of the ring that annihilates the entire module. And what we're going to do is suppose that the annihilator of our module M is generated by P to the R, where P is some irreducible element in our ring. For this special case, we want to show that this means that M is isomorphic to a direct sum of R, yi, but in particular, this is a direct sum where the elements are isomorphic to R mod P to the AI, where the biggest possible AI is going to be R itself. To start the proof, we know that M is a finitely generated module, which means there has to be a finite generating set. So let's let some set x1 to xn be a finite set that generates M. We're going to proceed by induction on the number of generators, so induction on n. The base case is n equals 1. Now if n equals 1, then the generating set has one element. In other words, M is equal to just the ring times that single element x1. So already we get this first part of the condition. And we also know that the annihilator of M is equal to P to the R. But we showed earlier that the annihilator of M is equal to the intersection of the annihilators of all of the generators. In this case, there's only one generator, so the annihilator of M is just the same thing as the annihilator of x1. And we said that x1 is annihilated by P to the R. So in this case, we've shown that Rx1, this is isomorphic to R mod P to the R. And therefore we've shown the base case n equals 1. As a side note, if you don't know why this particular relation is true, it's very similar to the idea of the orbit stabilizer theorem. So for groups, we know that if we have a group action, the orbit G times A, this is isomorphic to G mod the stabilizer of A. So in this case, we have a very similar situation. We have a module, and we say R times some specific element that's isomorphic to R mod. In this case, instead of the stabilizer, we're looking at the annihilator of that element, which is P to the R. Now it's time for the inductive steps, so let's suppose that n is greater than or equal to 2. Like we said earlier, we know that the annihilator of M, this is equal to P to the R, but it's also the intersection of the annihilators of all of the elements in here. So in particular, what that means is that the annihilators of each of these elements, the annihilators of xi, these have to equal P to the k, for k being less than or equal to R. And the reason for that is that if one of these annihilators had some different irreducible, if it looked like P to the k times q, where q is a different irreducible, then the intersection of all of these annihilators, it would have to be P to the R times q. you would need a multiple of q in there to annihilate that specific element. And so that would change this intersection. It would no longer be p to the r. So all of the annihilators have to be a power of p. And in particular, because the annihilator is p to the r and not some smaller power, there has to be one of the elements in here. Without loss of generality, I'm going to assume that it's x1. There has to be some element that has annihilator exactly p to the r. Because we know that all of the annihilators are powers of p, otherwise there'd be an extra irreducible in here. But because it's p to the r, if all of these annihilators were like p to the r minus 1, then the intersection would also be p to the r minus 1. So because the intersection is p to the r, one of them has to have annihilator exactly p to the r. So we're going to assume that one is x1. Now our goal here is going to be to show that m is isomorphic to rx1 direct sum with m mod rx1. In this case, we know that the quotient module over here, that's going to be generated, of course, by the original set of generators, because if they generate m, they're also going to generate all the cosets of m. But in the quotient module, we don't need x1 anymore, because x1 is equal to 0 in the quotient module. So this thing over here is going to be generated by x2 up to xn, which means it's generated by less than n elements. So we can use the inductive hypothesis on this quotient module. In particular, we know m mod rx1, this is going to be isomorphic to, by the inductive hypothesis, the direct sum of some ryi, and this is isomorphic to the direct sum of some r mod p to the ai. And from here, we want to use this information to try to show that m is the direct sum of these two things. I'll also point out for the inductive hypothesis to work that we know, since the annihilator of the entire module is p to the r, that p to the r times m equals 0. And therefore, in the quotient module, p to the r times m plus n, this is also equal to 0. So the annihilators of all of these generators in the quotient modules, these are also going to need to divide p to the r. If p to the r kills everything, p to the r has to be a multiple of the annihilator. And so the annihilators of all these generators are still going to be powers of p, which means the annihilator of the quotient module, the annihilator of m mod rx1, that's still a power of p. That's just necessary because that means we have all the conditions to apply our inductive hypothesis, so we know that this quotient module is going to be this direct sum. Now, if we can show this, if we can show that m is isomorphic to rx1, direct sum m mod rx1, then we're done, because we know that this quotient module is isomorphic in the form that we want. And of course we know, just like we showed in the n equals 1 case, that rx1 is cyclic and it's r mod p to the r. So as soon as we do this, we get the direct sum form for the entire module. rx1 direct sum this sum, or r mod p to the r direct sum this. And so that finishes the proof. All we need is to show this isomorphism, and then by induction, we're done. And this is the part where we're going to use the annihilator splitting lemma. We're going to get some map psi from the generators into the module such that these two conditions are satisfied, and then we'll know, like we showed at the beginning, that m is isomorphic to rx1 direct sum with m mod rx1, and then we're done. Notice that when we're looking at this function psi, there's no relation between the different inputs of psi. So there's nothing that we need to satisfy for psi of y1 plus y2 or anything like that. All of the inputs stay separate. So all we need to show is that we can construct this psi of yi that satisfies these conditions for each generator separately. As long as we know it's possible for each generator separately, we can construct the entire function one generator at a time. So let's take a specific yi. We know that each yi is an element in the quotient module. In other words, it's a coset. So we know that we can write the yi as some coset representative w plus rx1. Remember, rx1 is the submodule in this case. So here we've just taken w to be an arbitrary coset representative of yi. Now remember, we said earlier that because p to the r times m equals 0, we also know p to the r times m plus n equals 0 in the quotient module, so the annihilator of the quotient module has to be some power of p. And again, that annihilator is going to be the intersection of the annihilators of all of the yi's. In other words, each of the yi's is going to have an annihilator that's equal to a power of p. Let's call it p to the a, and a has to be less than or equal to r. So because of that, we know that p to the a times yi is going to be 0. So we can see what that means in the context of this equation. So p to the a yi, that's going to be 0. This is a coset, so remember 0 is the same thing as 0 plus rx1. And on the right side, we get p to the a times w plus rx1. So if we have p to the a times w plus rx1 being equal to 0 plus rx1, that's only possible if this element is inside of the submodule rx1. So we get that p to the a times w is an element of rx1, which means p to the a w is equal to lambda times x1, where lambda is some element in the ring. Now let's take a step back and remember where we're trying to go with this. We have this set of generators, these yi's, in the quotient module. And for any of these yi's, we want to find a coset representative such that if something annihilates the coset yi, then it also annihilates psi of yi. Now, we picked w as some arbitrary coset representative of yi. We know that we can reach any other element of this coset by adding some element of rx1. If we have some t in the ring, then every element in the coset is going to look like w plus tx1. Now, what we want is that we pick the right coset representative, the right t here, so that we have a w plus tx1, where if a annihilates yi, it's also going to annihilate w plus tx1. Now we said that the annihilator of yi is going to be a power of p that looks like this. So because this annihilates yi, we need it to also annihilate this, which is psi of yi. So we need p to the a times this to equal 0. Now if we take a look at this equation over here, we can see that it's pretty close to this result that we want. If we subtract lambda x1 on both sides, we get p to the a w minus lambda x1 equals 0. And that's almost here. We're almost here. We want to factor out a p to the a. But let's see what happens if we try to factor out a p to the a. If we do that, we're going to get p to the a times w minus p to the negative a lambda x1. Now, this equation is true if p to the negative a lambda x1 exists. But rings don't always have multiplicative inverses. So p to the negative a lambda is not necessarily an element of our ring. Notice that if p to the negative a lambda is an element of the ring, then if we use this as our t, we get the condition that we want. This is the coset representative that we need, the w plus rx1, and then the proof is over. But we need to figure out, does this p to the negative a lambda exist? Well, it's going to exist if lambda contains p to the a, if the factorization of lambda has p to the a in it. Because if it does, then we can always factor out that p to the a to the outside like we want, and then everything works out. So let's say we factor out the highest possible power of p that we can get from lambda. In that case, we're going to have lambda equals p to the s times b, where s is some integer. And our goal is to show that s is greater than or equal to a, so that we can factor out that p to the a. Now we're going to use some information from the original module. Remember that the whole module, the original m, is annihilated by p to the r. In particular, w is an element of m. So we know that p to the r times w, this is going to be equal to 0. Now, we know that a is less than or equal to r. So we can write p to the r times w as p to the r minus a times p to the a w. A is less than or equal to r, so r minus a, that's going to be greater than or equal to 0. Now in here, p to the a w we know is equal to lambda x1. So we're going to substitute that in. So we have p to the r minus a times lambda x1, but I'm going to use this form of lambda. We know that lambda is equal to p to the s times b. And then we have the x1 over here. Now if we look at this exponent, we have p to the r minus a plus x. So here, p to the r minus a plus s b x1, and this is equal to 0, like we said at the beginning. Now remember, we chose x1 in a very specific way. We know that one of the generators of m has the annihilator exactly p to the r, and we chose x1 to be that element. We chose x1 to be the element with annihilator p to the r. And this is why. Because we pulled out the highest possible power of p in this factorization of lambda, we know b doesn't have any powers of p in it, because otherwise we would have taken those out. The annihilator of x1 is p to the r, and this b isn't going to help us annihilate x1 because it's not a power of p. So the only way this is equal to 0 is if there's a p to the r in this part right here. So that means we have r minus a plus s has to be at least r in order to annihilate x1. And of course, we can cancel the r's on both sides, and then if we bring the a to the other side, this gives us s greater than or equal to a. And as a result, the power of p in lambda is going to be bigger than a, so we can pull out a power of p to the a, and s minus a is going to be greater than or equal to 0. So this is well defined, and that gives us our coset representative just like we want. So now we've shown that for every yi, we can get a coset representative with the property that we want, and therefore by the annihilator splitting lemma, we can write the module as rx1 direct sum with m mod rx1. And since this is already a direct sum of cyclic modules by the inductive hypothesis, we've proved our final result over here just like we want. Now this is only the proof for when the annihilator of m is a power of p. And that might seem like a very specific result. For a general module, obviously, the annihilator is not going to be just a power of some irreducible. But it turns out that if the annihilator is any sequence, any product of powers of irreducibles, we can split it up into the distinct irreducibles, and from there we can apply this result to break any arbitrary module down into a direct sum of cyclic modules. So now, instead of supposing that the annihilator of m is a power of some irreducible, we're just going to assume that it's generated by some element a. Remember that R is a principal ideal domain, and we know that the annihilator of m is an ideal in R, and therefore it's going to be principal, so it's generated by something. But this is not necessarily just a power of one irreducible. Now our goal is to show that m is isomorphic to some direct sum of m bracket p to the r. Now this notation here is a specific notation, and this is saying the set of elements of m that are annihilated by p to the r. So in this direct sum, we're going to have a bunch of different irreducibles here and a bunch of different powers, but each of these is going to be a subset of the original module, the subset of elements such that p to the r times m equals 0. And we are again going to prove this by induction. It's going to be a lot simpler actually than the original case. What we're going to do is let n be the number of distinct irreducibles in the factorization of a. And from there, we're going to proceed by induction on n. So the base case is n equals 1, And that's very simple because then the annihilator of m only has one irreducible in its factorization, so it's just p to the r for some p. And in this case, we know that every element in m is annihilated by p to the r because the annihilator is p to the r. So m is going to be equal to m bracket p to the r because the set of elements in m that are annihilated by p to the r is the entire module. So this is a direct sum with one factor, and that gives us the base case. Now, for the inductive step, we're going to do something different. Suppose we have n greater than or equal to 2. Then we know this annihilator A, this is an element in the ring, and we can take one of the irreducibles in A because we know it has at least 2. So say P is one of the distinct irreducibles in the factorization of A, and we're going to write A as P to the R times B. So in this case, again, we're factoring out the highest possible power of P, and therefore B is going to be an element with no powers of P in its factorization. It will be coprime to P. Our goal is to show that M is isomorphic to M bracket P to the R, direct sum M bracket B. And the reason is once we do that, we can apply the inductive hypothesis over here. Because we know that A has n irreducibles in its factorization. And when we do this, we take out one of the irreducibles. So this remaining part B is going to have n minus 1 irreducibles in its factorization. And we know over here, M bracket B, this is the set of elements in the module that are annihilated by B. So the annihilator of M bracket B is equal to B. And therefore we have this condition here. The annihilator of this module is equal to B, which has n minus 1 irreducibles. And therefore, by the inductive hypothesis, we can write M bracket B as a direct sum of M bracket some power of an irreducible. And therefore, we're done because we have this part, M bracket P to the R, direct sum a bunch of other things that look the same, and then we're done. So our new goal is to show that M is isomorphic to this direct sum. And in order to do that, we'll show that M bracket P to the R and M bracket B are complements in M. Now remember that we said B is coprime to P to the R. And therefore, there's going to be some P prime in the ideal generated by P to the R, and some B prime in the ideal generated by B, such that P prime plus B prime is equal to 1. This is because when we have these two elements being coprime in the ring, that means that these two ideals are co-maximal. In other words, we can take these two and add them to get 1. Now suppose we have some element M that's in the module. The first condition for complements is that we can write any M as a sum of an element in here and an element in here. But we know that the entire module is annihilated by P to the R times B. So P to the R Bm equals 0 for any element M in the module. In particular, we can write this as P to the R times Bm equals 0, or B times P to the Rm equals 0. So Bm is annihilated by P to the R, meaning Bm is in M bracket P to the R. And on the other hand, P to the R times M is annihilated by B, so this is in M bracket B. So if we can take some element M and write it as a combination of Bm and P to the Rm, then that's a combination of these two submodules, and that gives us our complement condition. The way that we do that is using this fact. For any M in the module, we can write M as, of course, 1 times M, but that's the same as P prime plus B prime times M. So this is P prime M plus B prime M. And we just showed that this first part is annihilated by B, and this second part is annihilated by P to the R. So this is an element of M bracket B for this first part plus M bracket P to the R for this second part. That gives us the first condition that we need for the complement. Now all we need to do is show that these two submodules only intersect at 0. So let's suppose we have some element m that's in both m bracket p to the r and m bracket b. We want to show that this means m is equal to 0. We're just going to use the exact same trick that we did for the first part. M is equal to p prime plus b prime m. This is p prime m plus b prime m, but we know that m is annihilated by p to the r, and therefore p prime m is equal to 0. We also know that m is annihilated by b, so b prime m is equal to 0. This is equal to 0 plus 0, which is just 0. So we've shown that if an element is in both of these submodules, that means it has to be equal to 0. We've satisfied both of the conditions, and therefore these two submodules are complements in M, so M is isomorphic to this direct sum. And by the inductive hypothesis, we are done. For any finitely generated torsion module over a PID, we can write M as the direct sum of M bracket P to the R. And we just showed earlier, of course, this submodule is going to have the annihilator P to the R. So we can split this up into that extra direct sum. So we have two direct sums on top of each other, and that's going to make us write every module as a direct sum of cyclic modules. So right here is the result that we just showed for finitely generated torsion modules over a PID. We can write M as a direct sum over some irreducibles of M bracket P to the R. And we can break this down even more, since the annihilator is P to the R. We can write it as the direct sum over P of the direct sum over some powers, A, of R mod P to the A. And when we look at this factorization right here, we call these elements P to the A the elementary divisors of our module. Now we know for distinct irreducibles, P and Q, that P to the A and Q to the B are co-prime, so they generate co-maximal ideals. And by the Chinese remainder theorem for rings, that means that R mod P to the A, direct sum with R mod Q to the B, is isomorphic to R mod P to the A times Q to the B. This is the intersection of these two ideals because they're co-prime. So we can use this to take the result that we have right here and transform it into a different form. So we do this in a series of steps. In the first step, for each irreducible, we're going to take the highest power in this direct sum. So there's going to be some R mod P to the A where A is as big as possible. We're going to take that part of the direct sum. And then we're going to take R mod Q to the B, where B is as big as possible. We're going to repeat that for all of the irreducibles, and then we're going to combine them like this using the Chinese remainder theorem. So we're going to have R mod P to the A, Q to the B, and so on for the highest power of each irreducible. We'll call that Fm. So this is going to be, Fm is this product of all the highest powers of the irreducibles in our direct sum. Now after that, obviously we're going to have a bunch of terms left in this direct sum. So what we do next is apply the exact same process to all the remaining irreducibles. So we apply this, we take the next highest power of each irreducible. And then that's going to give us, by the Chinese remainder theorem, R mod, that product we'll call Fm minus 1. And then we're going to keep doing this, keep applying the steps until we have no more irreducibles left. And then at the last step, it'll be R mod F1. And the reason this is useful is because Fm has the highest power of every irreducible, we know that Fm is going to be a multiple of all these other elements. In particular, we can write F1 divides F2, since F2 has higher powers of all the irreducibles. F2 divides F3, F3 divides F4, and so on all the way up to Fm. So this divisibility condition gives us some nice extra properties when we're working with this form of the module. And because these are very useful to work with, we call these factors f1 up to fm the invariant factors of m, and we call this version of m the invariant factor expansion. So that is how we can write every finitely generated torsion module over a PID as a direct sum of cyclic modules. We can either just use powers of irreducibles, these are called the elementary divisors, or we can put them together to get products of irreducibles down here with this divisibility condition, and then they're called the invariant factors.